Compound statements, or blocks, can be mixed to produce complex flow control to solve a wide range of problems. We will frequently mix for statements, including nested for statements, and if, elif, else blocks. Python relies on indentation to determine the scope of a compound statement, and so consistent indentation is essential. Code with more than 3 levels of indentation is challenging to read, and so best practice is to limit nesting and to use functions when more levels are needed. Start by opening Lesson 18's notebook. Run the first cell to load some data that we will use in the problems. The first statement asks us to mix a for loop and an if statement to create an asymmetric random walk. We've seen 3 types of compound statements: def, which starts a function, for, which starts a loop, and if, which performs conditional execution. These statements all use indentation to indicate scope. Other compound statements, such as exception handling and context managers, also use consistent indentation, where all code in the statement is indented, and dedented code is used to demarcate the end of the statement. When using nested statements, the level of indentation determines the execution scope. Varying indentation allows the scope to switch out of and back into a compound statement. Here we see an example of a deeply nested set of compound statements. The outer statement is a for loop that iterates across the contents of range 5, which is 0, 1, 2, 3, and 4. There are 2 lines that are in the direct scope of the loop: the if, the elif, and the print statement. The if block requires a deeper indentation, and there are 2 statements contained in the if block: another loop and a print. The contents of the inner loop is also indented. This loop contains a function definition, which has its body further indented. The call of the function is dedented, and the print statement finishes the loop. After this loop is executed, the print statement, if but not for, is then executed, and the if statement is completed. The else path is simpler and only contains a single statement. After either the if or the else has been visited, the print statement in the loop executes for each of the 5 iterations. When the loop over I has completed, the print statement finished is run once, since this is not indented, and so not in the scope of the outer loop. Start by importing NumPy. We create 100 standard normal shocks using np random standard normal followed by 100. We can use np0s 100 to create an empty array filled with zeros to hold our simulated random walk. We start by assigning e0 to y0 to initialize the random walk. Next, we use a for statement across a loop variable I in the range 1 to 100. We do not use 0 since we do not have a value for observation -1. We set the current value of y equal to its previous value. This and the other statements are in the for block and so are indented using for spaces. Then we use an if statement to check whether the current shock is negative. If shock is negative, we add 2 times the shock to the process. We dedent back to the scope of the for statement and then add the else statement. We then indent to indicate that we are in the scope of the else statement and add the shock when it is positive. We can use cumsum to construct the symmetric random walk as the cumulative sum of the shocks. The next cell contains a block that we can use to plot the 2 series. Copy this into a cell and run the code. We see that the asymmetric random walk is below the symmetric one. We do not actually need the if statement since we can use Boolean math. The setup for the simulation is the same, and we initialize the array to store the results, set the first value, and use the same loop declaration. We can simulate the same asymmetric random walk by adding an extra copy of the shock when it is negative by multiplying the shock by a Boolean expression that is 1 when the shock is negative. Note the essential use of parentheses here to ensure that the Boolean is computed before the multiplication. Plotting this version shows the result is the same. The second problem asks us to compute the length of runs, defined as periods where the sign of the return of the portfolio remains the same. We start by getting the number of observations using len. Len returns the size of the first axis in a NumPy array. We then set up the run variable using zeros with the same size. The run is initialized to 1. We then use a for loop over the range from 1 to the length of the data. The run is continued if the sign of the current return matches the sign of the previous return. We can get the sign using the function np.sign. When we have a sign match, the current value of the run is 1 larger than the previous value. If we do not have a match, then we reset the run length to 1 since this is the start of a new run. We can compute the length of the longest run using the max method. mp.where can be used to find the locations of the maximum. Here we see there are 2. We can use the code provided to plot the run lengths to see how they evolved. In Visual Studio Code, we can hover over a plot to open it in a plot viewer. Here we can zoom in and pan around the plot to take a closer look. Consistent indentation is essential for correct program execution. Most Python-specific editors, including VS Code and PyCharm, provide visual guides to highlight compound statement scope. The best practice is to limit nesting to 2 or 3 levels, which simplifies determining the appropriate scope of a statement.